All right, we are now going to move into something called simplifying radical expressions. If you've watched the previous two videos, you've seen we looked at what radical expressions are, how to evaluate them, how to evaluate them when we use a notation with fractions in the exponents. But the ones we've looked at have all come out nicely. We've been able to evaluate them or simplify them and get a nice whole number typically. By the end of this video, you will be able to simplify something that looks like this, right? Just so you know what's coming. You'll be able to simplify something that looks like the fourth root of 48 x to the fifth y to the 11th. That whole thing. So just so you know where we are headed. So keep that in mind. All right. So we're going to start this video with something that leads us into the thinking that's necessary to be able to do these problems effectively. So what I'm going to do is I'm going to give you a number, right? And your job, you're going to have to play along here. Your job is to take that number and write it as a product of two factors. And you have to write it as, give all the possible options. Here's what I mean by that. Besides 1 times 12, what are all the multiplication problems that give you 12? You might be coming up with 2 times 6 and 3 times 4. We need to make sure we get all of them, okay? Do the same thing for the number 18. Pause the video, do the number 18. In some order, you should end up with something like 2 times 9 and 3 times 6. Those are the only other options. Now do the same thing for the number 48. So do the same thing with the number 48. If you paused it and you're coming back to the video, you should have 4 different options. If you don't have all 4, pause it and see if you can figure out what that other ones are. You should get 2 times 24, 3 times 16, 4 times 12, and 6 times 8. All right? So that's the first part of this exercise. The next thing I want you to do is I want you to go through and look at all of these numbers that we came up with, every single list of numbers of factors, and find all of the perfect squares that you see anywhere in these lists here. So find all the perfect squares, scan them, look through them all, find them all. All right. So as I look through the 12 options, the only perfect square I see is this 4. As I look through 18, I only see one perfect square, and it is 9. As I look through the 48s, I see 2 perfect squares. Did you see both of them? They are 16 and 4. So we had 2 perfect squares. So we're going to come back to this momentarily. All right. So I'm just going to leave this there for a second. So what we're going to do now is we are going to simplify the square root of 12. Now, if you take your calculator and you try to evaluate the square root of 12, you're going to get this. 3.464101615313775, etc. You'll notice that this decimal number is never ending and it's never repeating. It even goes beyond what's shown in this calculator. This is called an irrational number. It's a number that can't be written as a fraction in any way. When we take square roots of non-perfect squares like 12, this is what we always get. That is not what we are doing in this lesson, in this video. We want to simplify this thing. This is going to involve a really important principle involving square roots that I'm going to jot this down here. The square root of A times the square root of B is equal to the square root of A times B. And this works both ways, okay? So what do I mean by that? I mean that if you have two square roots, you can, and you're multiplying them, you can multiply them together, multiply the numbers under the radicals. You can also separate them into, instead of one big radical, you can have two individual ones. You'll see why that's important in a second. So we have to simplify the square root of 12. The way we do that is by rewriting the number 12 as one of these two things, that we came up with earlier. And we have to use the one that has a perfect square as one of the factors. So we're not going to use this one. We're going to use this one. We're going to write this as 3 times 4. Okay? Then we treat it like this. We rewrite it again as the square root of 3 times the square root of 4. So we separate it into two individual radicals. Then we take the square root of the one that's a perfect square. So we take the square root of that, which is 2. And we put that number out in front, kind of like we would with a variable. We put this first, followed by any remaining radical. 2 radical 3. 2 times the square root of 3. Those are the same thing. 2 times the square root of 3, or 2 radical 3. This is our simplified expression. What we did here was we looked at the number 12, and we looked inside of it. We peeked inside of it, and we found that it had a perfect square as one of its factors. So we took the square root of that number and we pulled it to the outside. And we left the non-perfect square, the 3, we left that on the inside. This is our simplified version. Let's do that now with the square root of 18, this other number that we started with. So pause the video and see if you can apply this same thinking. So we look at our two options. We look for the one with the perfect square. This one, not this one. We're going to break 18 up into 2 times 9. We're going to separate it into two individual roots. And then we're going to take the square root of the one that's a perfect square and put that out front. So that's going to be a 3 out front, followed by the square root of 2. And this is our simplified expression. You can probably guess what's coming. Yeah, it's the square root of 48. Now, the square root of 48 had a number of options, and it had 2 that had perfect squares in them. Which one of those do we want? We want the biggest one. We don't want this. We don't want this. And we're not going to use the one with the smaller perfect square. We have to use the one with the bigger perfect square because it allows us to simplify it the most. Here's what that'll look like. We will take our square root of 3 times 16. We'll separate it into 2. Whoops, I said 2. I meant to write a 3. The square root of 3 times the square root of 16. And then we will take the square root of 16, which is 4, followed by radical 3. This stays in, and the 4 comes out. 4 radical 3. That right there summarizes the idea that we do in this entire lesson. All of the things that we do in this video, we're just going to be looking at variations of this moving forward, okay? So let's try something like the square root of 300. You try this on your own based on what we just did. The square root of 300. I'll keep going. This is a really big number, right? And if you do the process that we started here with, which was writing all of the factors of 300, right? What times what equals 300? There's a lot of them, right? 2 times 150, 3 times 100, 4 times 100, or sorry, 4 times 75. We're going to go a long way. So I suggest you start. The way you can start this is start with the lowest possible number, 2, and see if that divides into 300. And it does, 2 times 150. And then just keep going. And do that process until you get to a perfect square. As on the big side, right? The big number side. And you'll notice you got one right here. We could keep going, right? I could keep going in this list. 5 times 60, 6 times 50. I didn't even do this ahead of time. But I believe 8 is 8 divisible? No, not 8. 9, 10 times 30. 12. I believe that there's got to be more. 15 times 20. I think I might have missed one in there. But the point is, you're looking for the biggest possible perfect square. And we got one, right? We got one right here. 100 is going to be that biggest possible perfect square. Okay. So we're going to take our 300. We're going to separate it into 3 times 100. We're going to then break it into 2 different radicals. And then we're going to take the perfect square of that big one. The square root of 100 is 10. So we can say it's 10 radical 3. Okay. So these were all square roots, right? There was an implied 2 right there in each of these. But we can also do this with cube roots or other higher order roots. So let's try it. Let's do this cube root of 24. So to do cube roots, you might want to, off to the side on your paper, even jot down some perfect cubes. You don't have to go too big usually, but this could be a helpful exercise. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. Probably won't need to go bigger than that. So we need to do the cube root of 24. So we need to do the same thing we did earlier, which was say 24 is equal to what times what? 2 times 12, 3 times 8, 4 times 6, and that's it. Then we're looking through these lists for perfect cubes. We're looking for these numbers. And the only one I see is this 8. So we're going to ignore these options and just focus on this. We need to take the cube root of 3 times 8, which is the cube root of 3 times the cube root of 8. We can take the cube root of 8, which we know is 2. And so this will simplify to be 2, that's this thing, times the cube root of 3. This thing, 2 times the cube root of 3. So the idea here is the same. We're just using cube roots instead of square roots. Try one on your own. Let's take the 4th root of 48. The 4th root of 48. So pause the video definitely and see if you can try this one, because this is new. This will be a bit of a challenge. I'll keep going. I'm going to write down some of those 4th powers here. 1 to the 4th is 1. 2 to the 4th is 16. 3 to the 4th is 81. Probably not going to have to go higher than that. So we're going to look at the number 48. We actually did the number 48 earlier to start this entire lesson. We said it was 2 times 24, 3 times 16, 4 times 12, and 6 times 8. But because we are looking for a 4th root, we are only looking for these numbers right here. Do you see it? Yeah, it is that 16. It's the only one. So we are going to take this and separate it into the 4th root of, we're going to turn 48 into 3 times 16. We don't care about these other options. 3 times 16. We can then break it apart into the fourth root of 3 times the fourth root of 16. We know, based on this over here, that the fourth root of 16 is what? 2. And so we will say that this is 2 times whatever's left, the fourth root of 3. 2 times the fourth root of 3. The ones we've looked at so far have all been dealing with just numbers. This is a great place to actually pause and let this sink in, right? Let this sink in. Go take a little walk, take a break. Make up a couple of these on your own and try some of these. Because what we're going to move into now is simplifying radical expressions with variables. And this is going to change your thinking just a little bit. So we're going to do this now with variables. Okay. This is going to require us to use the product rule and the power rule, some of those exponential rules that we've used before. We're at least going to have to think about those as we are doing these problems. Okay. So let's start with this. The square root of x to the third. Okay. Now, if we apply the same reasoning that we did a minute ago, this is our base on the inside. So what are the different ways that you could multiply two things to get x to the third? You really only have one option, x to the second times x to the first, right? That's like the only option, okay? Then you're asking yourself, are either of these two things perfect squares? And hopefully you think, I think this one is, yeah. It says x squared. So what we're going to do is we're going to rewrite this as x squared times x to the first. We're then going to separate it just like we did before. X squared times times the square root of x. I'm going to leave off the 1. I don't need to write it here. I'm just going to leave it off. And then we can take the square root of this one, which is just x. The square root of x squared is x. Why? Because x times x equals x squared. So how do we simplify this? We put this out front, and then this stays on the inside. X radical x. X times the square root of x. X cubed had a perfect square of x squared built into it. We pulled that out, we took its root, and then we left this other x on the inside. I told you this was going to take you a little bit different thinking here. Let's try x to the 7th, the square root of x to the 7th. So this one's going to seem a little bit more challenging to you. So stay focused as we think through this. We need to break this up into something times something, right? And so we think about all the things that could make x to the 7th. How could we multiply two things together to get x to the 7th? Well, it would be x to the 6th times x to the 1st. Remember how we add exponents when we are multiplying? It could be x to the 5th times x to the 2nd, right? 5 plus 2 is 7. Or it could be x to the 4th times x to the 3rd, okay? So, again, 6 plus 1 is 7, 5 plus 2 is 7, 4 plus 3 is 7. We need to, as we've been doing, find the perfect squares, right? We have to look through these and find the perfect squares, and we specifically need to find the biggest one. Here's where you're going to need to pause and think about this. Any even numbered exponent on a variable is always going to be a perfect square. So this, and this are all perfect squares. This, and this are all perfect squares. You might be asking yourself, why? Because in each of those cases, we can take something and square it and get all of these as an answer, or each of them as an answer individually. Can you figure out what that would be for each one of them? So could we come up with something to fill in these boxes? Is something, this is probably the easiest one to do. Is something squared equal to x squared? Yeah, x squared is equal to x squared. Was something squared equal to x to the fourth? Yeah, x squared is equal to x to the fourth. Why? Because of that power rule. Remember how we multiply these numbers? Well, what about this one? What squared equals x to the sixth? Might need to stare at this one for a minute. What thing squared equals x to the sixth? X to the third. X to the third to the second is equal to x to the sixth because we would multiply these two things. So if we go back to what we're doing, we're trying to use the biggest perfect square, and it's always going to be the largest possible even exponent. The largest even exponent. That's what you're trying to do, okay? So what we're going to do is we're going to separate x to the seventh into x to the sixth times x to the first. We're going to then break it into two separate radicals, x to the sixth, and then the square root of x to the first. We're then going to take the square root of the even powered one. And what's that going to be? What's the square root of x to the sixth? It's always going to be half of it. It's always going to be half. That's why we pick an even exponent. The square root of x to the sixth is x to the third. So we have x to the third on the outside times the square root of x on the inside. Whew, these make you think. So let's do another one. The square root of, we're going to simplify the square root of x to the 13th. So we don't have to do this whole list thing, I promise you. You don't have to do this entire list every time. These, it's going to be a bit easier, actually. You are always, when you have an odd numbered exponent, you're going to start by just doing one less than whatever that number is, and 1. 12 times 1, or 12 plus 1 is 13. So x to the 12th times x. It's always just going to be one less. Always. So that's going to give us the square root of x to the 12th times the square root of x, which is, what do we do to simplify this now? I said it a minute ago. The square root of any even numbered exponent is always going to be half. X to the 6th. X to the 6th. And then it's followed by the square root of x. Okay. Yep. These are challenging. Let me have you try one more on your own. How about something crazy like x to the 97th? The square root of x to the 97th power. Pause the video. Try this on your own. I'll keep going. The principle remains the same. It's going to be the square root of x. We're just going to go one less than this. X to the 96th times x to the first. We are going to separate it. X to the 96th, x to the first, and then we take whatever this exponent is and we cut it in half. That's the thing that comes to the outside. X to the 48th, radical x. Okay? Pause in, give your brain a little break. These are challenging. What if I do multiple bases? So what do I mean by multiple bases? I mean, what if I put two variables on the inside? Let's go the square root of x to the 11th, y to the 10th. No, I don't like 10th. Let's make it y to the 8th. X to the 11th, y to the 8th. So what do? Well, we do the same thing, but we focus on each base individually. So let's start with x to the 11th. It's an odd numbered exponent, so we're going to break it up into x to the 10th times x to the 1st. Always go one less and then one. Y already has an even numbered exponent, so we're just going to leave it as y to the 8th. Now we take all three of these and we break them into, I'm going to write it beneath it, x to the 10th, square root of, and then square root of x, and then the square root of y to the 8th, right? I separated into three different things multiplied together. These two are perfect squares. So let's take their square root. It's always going to be half of whatever your exponent is, x to the 5th and y to the 4th. This one just stays as the square root of x. The only thing we have left to do to clean this up is put this part at the end. So we're going to have x to the 5th, y to the 4th, times the square root of x. We just brought this y out front with the x. So notice how we ended up, right? Y to the 8th was an even numbered power, so there's no y left on the inside. X was an odd numbered power, so it did have an x left on the inside. What if we put a number in there? Like the square root of 18x to the 9th. Can you do that? See if you can pause and figure out what happens here. I'm going to keep going. So we start with the number 18. We need to break this up. So one of the numbers is a perfect square. You might have come up with 2 times 9, right? 9 is a perfect square. Then we do the same thing with the x's. Because it's an odd numbered exponent, we're going to do x to the, we're going to go one less than 9, 8 times x to the 1st. Again, this is a perfect square. Now I'm going to break it up into 4 different radicals. The square root of 2 times the square root of 9 times the square root of x to the 8th times the square root of x. So it's all 4 of these individuals. I'm going to take the square root of the 2 perfect squares. So that's going to be 3 and x to the what? Cut it in half, 4th. And then these two just stay in their radicals. We now write it in a neat and tidy way. So we take these, we put them together out front as 3x to the 4th. And then we take the 2 that were in and we put them back together under one radical, radical 2x. So really, we were able to pull these things to the outside by taking their roots. And then these ended up staying on the inside. 3x to the 4th, radical 2x. Let's do one more of those. Try this one on your own. The square root of 20 x to the 2nd, y to the 5th. I'll keep going. I made 20 into 4 times 5. I left x squared alone because it's even. I made y to the 5th into the y to the 4th times y to the 1st. I broke this up into 5 separate radicals. This radical 4 times radical 5 times radical x squared times radical y to the 4th times radical y. I took the square roots of the ones that I could. This is a square root, a perfect square, so it's radical 2. This is not, so I leave it as it is. This is, so I make it an x. These are all times, times, times. I take half of the even numbered one, y squared. I leave this y inside. Then we put it all back together. 2xy squared is out front. And then our two radicals get put back together, radical 5y. 2xy squared times the square root of 5y. So lastly, the last thing here is we are going to look at the same thing, but now with some higher order roots. Same thinking, but instead of square roots, we're going to be looking at maybe third or fourth roots. So let's start simple. Let's start the cube root of x to the fifth. Cube root of x to the fifth. Now, let's think through this. We need to break our x to the fifth up into some multiplication problem. Let's put all the options out here. X to the fourth times x to the first, x to the third times x to the second. Those are the things that could make x to the fifth. But we're not looking for square roots anymore. We're looking for cube roots. What does that mean in terms of our exponents? We want to find, for cube roots, the largest multiple of whatever that root is. In this case, it's 3. The largest multiple of 3. In this case, do you see it? It's just 3. So what does that mean? We're going to separate this into these two. The x cubed times x squared. And then just like before, we will break it up into two separate radicals, x to the third times x to the, square root of x to the second equals. So I forgot to put my cube symbol up there. We're taking the cube root of all of these. That is definitely important here, the cube root. So what is the cube root of x cubed? We're always, instead of cutting them in half here, we're taking this exponent and dividing it by whatever that root is. We're dividing it by 3. The cube root of x cubed is just x. So the x comes out to the front from here, and this all stays the same, times the cube root of x squared. Again, x to the fifth, the cube root of x to the fifth. We found this x to the third inside of it. We took its cube root, which was x. We put that out front. We left the cube root of x squared on the inside. So what we're going to be doing then is always looking for, with exponents, the largest possible multiple of whatever that root is. Let's try another one of the cubes. Let's try the cube root of x to the 17th. Pause the video and see if you can figure this out. See if you can do this just like the previous one. I'm going to keep going. So we have to separate x to the 17th into x to the something times x to the something. They have to add up to 17 because of that product rule. So what's the largest possible multiple of 3 that's less than 17? What are multiples of 3? 3, 6, 9, 12, 15, 18. We want x to the 15th. We have to have a multiple of 3. What's that going to be with? X to the second, because they have to add up to 17. So that means we are going to have the cube root, sorry, I forgot to write it again, the cube root of x to the 15th times the cube root of x to the second. We can take the cube root of x to the 15th by doing what? Dividing our exponent by whatever our root is. This is going to simplify to be x to the 5th, which means we have x to the 5th on the outside of our radical. and the cube root of x to the second still on the inside. X to the fifth times the cube root of x to the second. We can do this with multiple bases as well. We've got two more for us to look at here. Let's go the cube root of 16x to the 19th. Pause the video, see if you can try it on your own first. I'm going to keep going. I'm going to just start writing bigger because these take up more room. So let's start with the number 16. We have to take 16 and break it up into the factor options. 2 times 8, 4 times 4. I think that's it. But we're looking for a perfect cube. 8 is a perfect cube. So we're going to make 16 into 2 times 8. For the variable times, I've got to separate this. X to the something times x to the something. And we need it to be the biggest possible multiple of 3 that's less than 19. 3, 6, 9, 12, 15, 18. We need an x to the 18th times x to the first. The exponents still add up to 19. We're taking the cube root. Now we can separate it into 4 individual smaller radicals, just like we've been doing. And we're going to take the cube roots of the ones that are perfect cubes, which would be this one and this one. The cube root of 2 stays. This is now 2. Cube root of 8 is 2. Remember what this one is? It's x to the 6th. We're always going to divide our exponent by whatever our root is. And then this one we're going to leave. Cube root of x. We take the simplified ones, we put them out front, 2x to the 6th. And then we put the remaining ones on the inside. Cube root of 2x. And the last one I'm going to do is the one I gave you at the very beginning of this lesson. Do you remember what that one was? I said by the end of this, you will be able to simplify the 4th root of 48, x to the 5th, y to the 11th. So can you try this? I know this is really challenging, but give it a shot, try it first, and then come back and watch what I do. So we have a number and 2 variables to figure out here. 48. We need to break it up into 2 numbers, and one of them has to be some number to the 4th power. I can't figure out those in my head. I'm going to have to jot those down first. 1 to the 4th is equal to 1. 2 to the 4th is equal to 16. 3 to the 4th is equal to 81. I won't have to go any higher than that because my number is a 48. So, have you figured out what it is yet? The number 48 can be broken up into 3 times 16. And 16 is a 4th power, number to the 4th power. Y to the 5th, or x to the 5th. So when we're dealing with variables and their exponents, we have to get the biggest possible multiple of whatever the root is. Biggest possible multiple of 4 that's less than 5. In this case, it's going to be x to the 4th times x to the 1st. Remember, your exponents still have to add up to 5. What about the y? For the y, it's going to be times y to the, did you get y to the 8th times y to the 3rd? 8 plus 3 is 11. And 8 is the biggest possible multiple of 4 that's less than 11. So if we break it up into individual roots, the 4th root of 3 times the 4th root of 16 times the 4th root of x to the 4th times the 4th root of x times the 4th root of y to the 8th times the 4th root of y to the 3rd. We will take the 4th roots of 16, x to the 4th, and y to the 8th. We will leave all of the other things on the inside. The 4th root of x of 16 is 2. The 4th root of x to the 4th is x. And the 4th root of y to the 8th is y to the 2nd. We're always dividing the exponents by the roots. So that's what each of these will be. And then this, and this, those are just going to come back together under the radical. I'll just jump right to that part now. So this, and this are coming outside. 2x, y to the 2nd. And then the things we could not simplify, 3x and y to the 3rd, those all stay on the inside. And that is how we are simplifying radical expressions, particularly with things that are not perfect squares or perfect cubes.